In April of 2025, a team of scientists announced they had found the strongest evidence of alien life ever recorded, and for about 48 hours, it felt like the entire world stopped to pay attention. Then, something happened that almost never makes it into the headlines the first time around. Other scientists checked the data for themselves, and the story got a lot more complicated. What happened next says almost as much about how real science actually works as it does about the planet at the center of the whole controversy. Stick around, because this is one of the most fascinating examples in recent memory of what happens after a big claim gets made and the entire scientific community starts pulling it apart piece by piece. And if you want to keep following stories like this one as they develop, go ahead and subscribe before we get into it. The planet at the heart of this story is called K2-18b, and it sits about 124 light years away from Earth, orbiting a small, cool red dwarf star. It's considerably larger than Earth, roughly between the size of our own planet and Neptune, which puts it in a category astronomers call a sub-Neptune, a type of world that doesn't actually exist anywhere in our own solar system. What makes K2-18b interesting isn't just its size, though. It orbits its star at just the right distance to sit inside what's called the habitable zone, the region where temperatures could theoretically allow liquid water to exist on a planet's surface. That distinction matters more than it might sound like at first, because K2-18b's star is a red dwarf, a type of star considerably smaller, cooler, and dimmer than our own sun. Red dwarfs are actually the most common type of star in the entire galaxy, and because they burn so much cooler than a star like the sun, their habitable zones sit much closer in, meaning a planet can orbit tightly around one of these stars and still receive a temperature range compatible with liquid water. That also makes red dwarf systems unusually convenient targets for telescopes like Webb, since a planet orbiting close to a small, dim star tends to produce a clearer, more easily measurable signal when it passes in front of its star and starlight filters through its atmosphere on the way to us. Back in 2023, using the James Webb Space Telescope, researchers led by Niku Madhusudan at the University of Cambridge studied this planet's atmosphere and found something genuinely exciting: clear signs of methane and carbon dioxide, detected with strong statistical confidence. That same data also contained something much fainter and much more tantalizing, a weak hint of a molecule called dimethyl sulfide, usually just called DMS. Here on Earth, DMS is not some exotic laboratory chemical. It's produced almost entirely by living organisms, mostly marine phytoplankton drifting through the oceans, which release it as part of their normal biological processes. Scientists have spent well over a decade studying DMS specifically because it's considered one of the more promising biosignature gases available, something that, at least based on everything we understand about chemistry here on Earth, essentially requires life to produce it in any meaningful quantity. So when that first faint signal showed up in the 2023 data, it caught everyone's attention immediately, even though the researchers themselves were upfront that the detection was weak, sitting at only about 2 sigma of statistical confidence. To put that in perspective, 2 sigma means there's roughly a 5% chance the signal was just a random fluctuation in the data rather than something real. That's nowhere near strong enough to call it a discovery. It was, at best, an interesting hint worth chasing down with better data. So that's exactly what the team did. They went back to the James Webb Space Telescope and pointed a different instrument at the planet, one that observes a different range of wavelengths than the original observations had used. The first round of data, back in 2023, had come from 2 of Webb's instruments, called NIRISS and NIRSpec, both of which are tuned to study near-infrared light. For the follow-up observations, the team instead used an instrument called MIRI, the telescope's mid-infrared spectrograph, which studies a longer, different slice of the light spectrum entirely. The appeal of using a completely different instrument was straightforward. If the same molecular fingerprint showed up independently in a totally separate wavelength range, gathered by different hardware with its own separate quirks and calibration issues, that would make it much harder to dismiss the result as some kind of one-off fluke tied to a single instrument's particular blind spots. And in April of 2025, they announced their results. Using this new mid-infrared data, the signal for DMS, or possibly a closely related molecule called dimethyl disulfide, or DMDS, had climbed to roughly 3 sigma of confidence, meaning there was now only about a 0.3% chance the pattern showed up purely by accident. The concentration of these molecules in the atmosphere also appeared to be startlingly high, on the order of tens of parts per million, several orders of magnitude greater than the levels of DMS found in Earth's own atmosphere. Madhusudan and his colleagues described this as an independent line of evidence, gathered using a completely different instrument and a different slice of the light spectrum than their original 2023 observations, with no overlap between the 2 datasets. In their own words, the signal had come through strong and clear. Headlines around the world picked up the story almost instantly, many of them running some version of the phrase, strongest evidence yet of alien life. And it's worth saying clearly, the researchers themselves were careful, at least in their published paper, to stress that this was not a confirmed detection of actual living organisms. It was, in their view, a possible biosignature, a chemical fingerprint that on Earth is essentially only produced by biology, but one that would still need far more evidence before anyone could reasonably call it proof of life somewhere else. That distinction between a possible biosignature and confirmed proof of life is one of the more important nuances that tends to get flattened once a story like this moves from a peer-reviewed journal into a news cycle. A cautious sentence buried on page 6 of a scientific paper, carefully hedged with words like tentative and possible, doesn't translate especially well into a headline, and by the time the story had been shared, summarized, and re-summarized across enough outlets, a good portion of the public came away with the impression that scientists had essentially found aliens, which was never actually what the paper claimed in the first place. That careful framing, though, mostly got lost in translation once the story hit the wider public. And almost immediately, other scientists in the field started raising serious questions, not necessarily about whether life exists on K2-18b, but about something even more fundamental, whether the data actually showed what the original team claimed it showed in the first place. Here's where the story takes its first real turn. Because a claim this significant was always going to attract intense scrutiny, multiple independent research groups went back and reanalyzed the exact same publicly available James Webb data, using their own separate methods, their own statistical frameworks, and, in some cases, entirely different assumptions about how to process the raw instrument readings. And the results were, to put it mildly, not consistent with the original announcement. One team led by researcher Jake Taylor found no statistically significant evidence for either DMS or DMDS at all once they applied their own analysis. Another group led by Raphael Luque came to a similar conclusion, arguing that the supposed signal wasn't uniquely tied to those two specific molecules in the first place, since several other sulfur or carbon-based compounds fit the same data just as well. A team led by Luis Wellbanks took what's called an agnostic approach, meaning they didn't assume ahead of time which molecules should be present. And they too concluded that the current data simply couldn't robustly pin down any specific biosignature gas, since the same spectral pattern was equally consistent with a range of entirely non-biological molecules. Perhaps the most striking reanalysis came from a team led by Kevin Stevenson, which dug into something surprisingly technical but genuinely important: exactly how the raw telescope data gets grouped together before scientists ever run their statistical models on it. Different research teams sometimes choose slightly different ways to bin or group the thousands of individual data points a telescope collects across a range of wavelengths, and it turns out that choice matters a lot more than most people would expect. Stevenson's team tested a wide variety of these binning approaches and found that the specific method the original 2025 paper had used was one of the only ones that actually supported a DMS or DMDS detection. Using their own preferred approach instead, the supposed biosignature disappeared in the vast majority of their tests, roughly 87.5% of the time. Their conclusion was blunt. What looked like a promising astrophysical signal in the mid-infrared data was more likely explained by unresolved instrumental noise, essentially subtle imperfections and fluctuations baked into the telescope's own hardware and data processing pipeline, rather than any real chemical signature coming from the planet's atmosphere itself. Yet another study, this time using a genuinely enormous approach, searched through a library of more than 600 different molecules to see which ones could plausibly explain the same spectral features the original team had attributed specifically to DMS and DMDS. That search turned up a wide range of alternative candidates that fit the data just as well, including compounds that have nothing to do with biology whatsoever. In other words, even setting aside all the questions about whether the statistical signal was real or just noise, there was also a serious problem with uniqueness. The particular chemical fingerprint being pointed to as evidence of life wasn't even clearly distinguishable from a whole list of other entirely mundane possibilities. None of this back and forth means the original research team simply made a mistake out of nowhere, or that anyone acted in bad faith. Science, especially at the extreme edge of what our instruments can currently measure, often works exactly like this. A team gathers genuinely difficult, extremely faint data, applies a defensible method, and reports what they find, clearly labeling it as tentative. Other teams then test those same results using different assumptions, different tools, and sometimes entirely different statistical philosophies. And the original claim either survives that gauntlet or it doesn't. In this particular case, across nearly every major independent reanalysis published in the months that followed, the claim did not hold up especially well. As one prominent astrobiology paper on the subject put it directly, Current data on K218b simply does not meet the standard of evidence required to support a genuine detection of biosignatures. It's worth pausing here to explain why scientists set the bar so incredibly high for a claim like this in the first place, because it might seem almost frustratingly cautious from the outside. In physics and astronomy, the gold standard for calling something a confirmed discovery is what's called 5 sigma confidence, a threshold so strict that it corresponds to roughly a 1 in 3.5 million chance of the result being a random fluke. The original 2023 hint of DMS sat at only about 2 sigma. The 2025 announcement pushed that up to roughly 3 sigma. Both numbers sound impressive in casual conversation, but neither one comes remotely close to that 5 sigma bar. Researchers involved in the original study have actually said publicly that with somewhere between 16 and 24 additional hours of telescope observing time, they believe they could push the measurement up to that 5 sigma gold standard one way or the other, either confirming the signal is real with overwhelming statistical confidence, or ruling it out entirely. As of now, that additional observing time either hasn't happened yet or hasn't produced a clear public resolution, which is exactly why this entire story remains genuinely unsettled rather than closed. There's also a deeper scientific wrinkle sitting underneath all of this that goes beyond simple statistics. Even if future observations do confirm, at high confidence, that DMS or DMDS really is present in K2-18b's atmosphere, that still wouldn't automatically prove the presence of life. Researchers studying potential abiotic, meaning non-biological pathways for producing these same molecules, have proposed several chemical processes that could theoretically generate them without any biology involved at all, particularly in the kind of hydrogen-rich atmosphere K2-18b appears to have. Separately, other scientists studying the planet's broader chemistry have argued that its atmospheric composition could be explained reasonably well by an oxygen-poor sub-Neptune world that doesn't require a liquid water ocean or any biological activity whatsoever to account for what Webb has measured so far. Even the broader idea driving much of the original excitement, that K2-18b might be a so-called Hycean world, meaning a planet with a global ocean of liquid water underneath a thick hydrogen atmosphere, remains a genuinely contested interpretation rather than a settled fact, with multiple research groups pushing back on different pieces of that picture using their own independent modeling. So where does all of this actually leave things right now? K2-18b remains one of the single most intensely studied exoplanets in the field, specifically because of how much attention this biosignature claim generated, and that attention has, in a strange way, been genuinely productive. It's pushed multiple independent teams to develop and publish more rigorous methods for analyzing this exact kind of faint atmospheric data, methods that will end up being useful for studying plenty of other exoplanets in the years ahead, regardless of how this particular debate eventually resolves. But as things stand, based on the current published literature, the claim that scientists have confirmed strong evidence of alien life on this planet simply isn't accurate. What actually happened is closer to this. One team reported a tentative, statistically modest signal using a defensible but ultimately disputed method. A wave of other researchers then reanalyzed the same public data using different assumptions and largely failed to reproduce that same result, in several cases attributing the original signal to instrumental noise or to a range of non-biological molecules that fit the data equally well. The overall scientific consensus, as it stands today, leans toward there being insufficient evidence for a genuine biosignature detection on K2-18b, though the case is still considered open enough that additional observing time could meaningfully shift the picture in either direction. That might feel like an unsatisfying place to leave a story that opened with the phrase, "strongest evidence of alien life ever recorded." But it's actually a pretty good example of science functioning exactly the way it's supposed to. A bold, exciting claim gets made. It gets tested, challenged, and picked apart by people with every incentive to find the truth rather than protect anyone's reputation, including their own. And instead of settling for a headline that felt good in the moment, the field as a whole moved toward a more careful, more honest picture of what the data can and cannot actually tell us. Along the way, we got a genuinely fascinating case study in exactly how difficult it is to prove something as extraordinary as life on another world, and just how many careful, skeptical eyes a claim like that has to survive before it earns the right to be called a real discovery. If you want to keep following this story as new observing time comes in and the debate over K2-18b continues to develop, make sure you're subscribed with notifications turned on. Drop a comment letting me know whether you think this planet is hiding something or whether it's simply a case of noisy data getting oversold. And share this with anyone you know who's ever wondered how a headline claiming to have found alien life can quietly turn into one of the most debated scientific disputes of the decade.